Okay, so we're going to continue our discussion of gases, and we're going to delve into a particular situation because all the examples that we have looked at so far, we were dealing with, one pure gas in a container, and we were looking at the different properties of just that pure gas. What we'll be talking about here is a situation where we're encountering a gaseous mixture. And Dalton's law of partial pressures deals with such a situation. So as stated here, this law is used when it comes to dealing with mixtures of gases. And basically what this law says is that the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures exerted by the separate gases. Oh, by the way, before I forget, let me oops. Let me stop sharing for a minute. Let me check something out. Okay, I'm going to turn on my video. All right, so going back to sharing my screen. Okay, so as I was saying, this law deals with a mixture of gases, right? And let me go to full screen here. And basically what this law says, as I was saying earlier, is that basically the mixture, the total pressure of the mixture of gases is equal to the sum of the individual pressures exerted by the separate gases. So we can represent that relationship according to this equation here. P total is equal to pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3 and so on and so forth, all right? So when we're talking about the partial pressure, what we're talking about is the pressure that a gas would exert if it were the only gas in a container. And basically the assumption is that each gas in a mixture will behave as if the other gas is not present in terms of the influence or the pressure that it exerts on the walls of the container it's in, all right? Which falls in line with the kinetic molecular theory, because the kinetic molecular theory, among other things, says that the gas particles are acting independently of each other. There are no intermolecular forces between the gas particles. So therefore, the pressure of each of these gases would be the same, regardless of whether or not they are combined with each other or they're in separate containers. So therefore, we can write down an equation for each of these pressure terms based on the ideal gas equation, right? So the pressure for gas 1, P1, is equal to N1, the number of moles of that gas, times RT over V, right? So the temperature would be the same, the volume would be the same for all the gases in that mixture because they're in the same container, right? The only difference would be possibly the number of moles. So therefore, this is the equation for gas 1. This is the equation for the pressure for gas 2 and for gas 3 and so on. Now, we can actually play around with this to get some interesting relationships. So what I'm going to do is I'm going to go to my writing pad. Let me try this one here. And let me, okay, what's going on here? Let me scroll this down. And let me see if I can expand. Okay, let me work with this here. So as I said before, P1 is equal to N1 RT over V1. P2 is equal to N2 RT over V2. I'm sorry, V1 and V2 would be the same, so I don't need to make any distinction between them, all right? So continuing, P3 would be equal to N3 RT over V, and so on to Pn is equal to NN RT over V, right? So remember now, Dalton's law says that PT is equal to P1 plus P2 plus P3 all the way to Pn, all right? So what I'm going to do is substitute each of these terms here by their expressions here, right? So P1 will be replaced by N1 RT.
See what you're doing.
Oh, I'm sorry. I thought I shared my screen. It says Well, it actually says you're sure you're not seeing what I'm writing down?
No.
Okay, I don't know what's going on here because according to this, my screen is being shared. So what I'm going to do is get out of this and redo what I just, okay. So let me go here. Oh, I think I know what happened. Okay, I know what happened. Can you see my screen now?
Yes.
Okay, good. I'm sorry about that. Okay, so let me kind of recap what I was saying earlier. So what I was saying was that these are the individual expressions. These here are the individual expressions for the separate gases, the pressures for the separate gases in the mixture, all right? And according to Dalton's law, the total pressure will be equal to the sum of the partial pressures, right? So what I'm doing is substituting each of these partial pressure terms by these expressions right here. So for P1, I'm going to put N1 RT over V plus for P2, N2 RT over V plus for P3, N3 RT over V, and then that continues to Pn, which is NN RT over V. All right, and we can simplify this by factoring out RT over V. And what you're going to end up with is N1 plus N2 plus N3 plus all the way to NN, right? So we can simplify this further by basically replacing all the sum of the moles here by NT, right? So therefore this equation now becomes NT RT over PV, over V, I'm sorry. Let me erase this here. So V, all right? So this equation here, PT, we can calculate the total pressure of a mixture of gases if you know the sum of the moles, or if you can figure that out. If you're given the moles of all the gases in the mixture, you just add them up and that gives you the sum of the moles here, which is this right here, times R times T divided by V, and that will give you the total pressure of a mixture of gases. So that is derived from combining the combined gas law with Dalton's law, right? As a result of combining the combined gas law with Dalton's law, we end up with this expression right here, all right? Okay, any questions about this? Any questions? Any questions? Okay, so let me go back to the PowerPoint here. Can you see my screen again?
It's on the whiteboard.
What's that?
It's still on the whiteboard.
Okay, I think I figure out what's going on here. So let me do this. It looks like you have to be specific about what you want to show when it comes to the screen sharing. And it's something that I've just recognized is happening recently. I don't know why. I don't know if it's a change by the company. Anyway, okay, can you see my screen now?
Yes.
Okay, good, all right. So, so that's basically Dalton's law of partial pressure in combining with the ideal gas law. Okay, why is this thing not moving? Everything is going wrong today. Okay, so this is a pictorial demonstration of the partial pressure, the Dalton's law concept. So here we have two gases in separate containers. They're both at the same temperature and volume, right? But the difference is that the number of moles of hydrogen here is 0.6 and the number of moles of helium here is 1.50 moles, right? So basically, even though the volume and the temperature are the same in both cases, because the number of moles are different, that means that the pressures will be different. So if we combine both these gases in the same container, again at the same temperature and volume, then basically we can determine the number of moles, and we can also determine the total pressure which would be the sum of the separate pressures exerted by the individual gases, all right? So that's basically how pressures, provided that the temperature and pressure or the temperature and volumes are the same. And I think I should have made mention of that. Let me see if that was made mention of here. Okay, that's not made mention of here. So that's a very important point to make, that the volume and the temperatures of the gases must be the same in order for Dalton's law to hold true. All right. Okay. This is just pointing out the different values for the pressure of hydrogen and the pressure of helium and the total pressure when you're adding. Now, here's a question that is being asked based on the same idea right here. The question says, what would be the total pressure if 0.90 moles of nitrogen were added to the gaseous mixture in C? So here we have C, right? We already have 2.10 moles of gas here, right? And the question is asking, what if you added 0.90 moles of nitrogen to this mixture? What would be the total pressure? So I'm going to throw that question to you. How would you tackle this problem? Anybody? You have the total, you have the moles here already for hydrogen and helium. You have the total pressure here. And the question is asking, what would be the total pressure if you add an additional 0.90 moles of another gas, nitrogen, to that mixture? So how would you determine the total pressure?
Would you just add 0.90 to 2.10?
Okay, that's a good start. So where am I going to fit this? Okay, so the total moles would be equal to 0.90 moles plus the 2.10 moles. So that will give you 3.00 moles. Okay, so that's a good start. So what's the next step? Remember, the question is asking for the total pressure. So what's the next step?
To divide by the volume.
You're partially right.
Would you need to add 0.60 plus 1.50? Oh no, never mind. We already got that.
Yeah, that's what. Yeah, that's already done already, because that's the point. That's the point. That's the 2.10 that we have here.
Okay.
Yeah, but now that we have this, what will be the next step? Let me give you a little. Oh, I'm sorry. Go ahead. You're gonna say
that RT part, right?
Okay. So what's the equation you're going to use?
That's what I'm not sure of.
Anybody want to take a stab at it? There's an equation that you're going to use which will involve the total number of moles. I just showed you that equation on the previous slide. Or on the previous, not the slide, I'm sorry. On the writing pad that I did my derivation. I derived an equation. The equation started off with PT. PT is equal to what?
10.1.
No, the equation. I'm asking for the equation.
Oh, PT
N plus RT
to
divided by V.
NT RT, oops, T divided by V, right? So the NT is the total moles that we determine here. 3.00 moles times R, which is always 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is, what's the temperature in this question? 20 degrees. So you have to add 273 to 20, so that's 293 Kelvin, divided by the volume, and the volume is 2.0 liters. No, 5.0 liters, I'm sorry. 5.0 liters, all right? So let me get my cheap calculator here. So that is 3 times 0.0821 times 293 divided by 5.0. And according to my calculations, this works out to be equal to 14 point, how many sig figs? 2 sig figs, so 14. And the units would be atmospheres, because mole is going to cancel out here and here, Kelvin cancels out here and here, liters cancels out, so the only unit remaining would be the atmosphere unit. So that's basically how you do that problem. Okay.
Where did you get 0.0821 from?
That's a molar gas constant. Remember I showed you that from the ideal gas law.
Okay.
is equal to 0.0821, and that doesn't change, right? And the unit for that is liters, atmospheres over mole Kelvin. So the value of R is always going to be that value.
Where did you find the temperature and the volume?
The temperature and the volume is right here. 20 degrees, which you have to convert to Kelvin, and the 5.0 liters.
Okay.
All right. Okay, any other questions before we move on? Any other questions? All righty. Okay, so here's an example. Okay, so the question says, let's see what it says here. It says that you have a 1.0 liter sample of dry air at 25 degrees Celsius. It contains 0.0319 moles of nitrogen, 0.00856 moles of oxygen, 0.000831 moles of argon, and 0.00002 moles of carbon dioxide. And the question is asking for you to calculate the partial pressure of all the gases in the mixture and the total pressure of the gaseous mixture. So basically, you're going to be, and let me just warn you, this is going to be a bit tedious, but you're going to be using this equation. P for the gas is equal to nRT over V. And basically, you'll be using this equation for each of these gases, right? So you're basically going to repeat the same thing over and over again. So let's do this for nitrogen. The partial pressure of nitrogen is going to be the number of moles of nitrogen, which is given as 0.0319 moles, times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 25 degrees Celsius, which is 298 Kelvin, all divided by the volume, which is 1.00 liters, 1.00 liters. And let me work that out. So that's 0.0319 times 0.0821 times 298 divided by 1 liter, which is, according to my calculations, and folks, again, please check my calculation just to make sure that I'm on the right track, because I could be wrong. I'm not perfect by any means. So make sure that you follow along with me and check to make sure that I'm doing the right thing, all right? But according to my calculations, this works out to be equal to 0.78 atmospheres, all right? And then we're just basically going to do the same thing for oxygen, which is 0.00856 moles times R, which is 0.0821 liters atmospheres over mole Kelvin times 298 Kelvin divided by 1.00 liters. Oops, 1.00 liters. And according to my calculations, let me do this here now, 0.00856, shoot, 0.00856 times 0.0821 times 298 divided by 1, which is, according to my calculation, this gives you 0.209 atmospheres. And then we do the same thing for the third gas, which is argon. So here we're going to write partial pressure of argon is equal to, okay, what's the moles? 0.00031 moles times R, which is 0.0821 liters atmospheres over mole Kelvin times the temperature, which again is 298, and the volume is 1.00 liters. And let me do the calculation. So that's 0.00381 times 0.0. Okay, what did I do wrong here? Let me do this again. 0.00381 times 0.0821 times 298 divided by 1. So according to my calculations, and you need to round this off to 3 sig figs. So according to my calculation, this would be 0.0932 atmospheres. And then Okay, I'm going to squeeze the third or the fourth gas up here. And that fourth gas is carbon dioxide. So the moles here is 0.40, 1, 2, 3, 4, and then 2 moles times 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 298 Kelvin, divided by, how am I going to do this? Divided by 1.00 liters. So let me do that calculation, 0.00002 times 0.0821 times 298 divided by 1. Okay, so according to my calculations, this works out to be equal to, hold on, something is not looking right here. Let me try this again. 0.0002 times 0.0821 times 298. Okay, so that is right. So according to my answer, according to my calculation, the answer is how many sig figs? Okay, so this is 1 sig fig. So this is going to be 5 times 10 to the minus 3 atmospheres, all right? And then we have to add this up. And when we add them up, we have to round off to the lowest number of decimal places. So I'm going to, hold on, let me see. I'm going to put the sum down here. So I'm going to add this to this to this to this. And the reason why I'm doing that is because the question is asking for the total pressure. We just calculated the partial pressure of all the gases, right? But now we need to determine the total pressure, which would be the sum of these, all right? So let me do that. 5 times 10 to the minus 3 plus 0.780 plus 0.209 plus 0.0932. And in this case, we need to round off to, let me make sure I'm doing this right. I think I made a mistake when I was putting this in my calculator. 5 times 10 to the minus 3 plus 0.780 plus 0.209 plus 0.0932. Okay, so according to my calculations, rounded off to 3 sig figs, the total I'm going to put down here is 1.09 atmospheres. Okay, so that should be the correct answer. All right. Okay, any questions about this particular example? Any questions? Any questions? Okay, very good. So let's move on to a discussion of another concept, mole fraction. And mole fraction is basically a way of expressing, well, one could look at it as a way of expressing the concentration of a substance in a mixture of substances, right? In fact, this concept of mole fraction not only applied to gaseous mixtures, but pretty much any other mixtures, all right? But in this chapter, since we're concerned with gases, we're going to apply it to gases in this case, right? So let's define what we mean by mole fraction. So here, what you see on the screen is a definition of mole fraction, right? So here it's talking about the mole fraction of a gas, but as I said before, it can apply to any mixture. So the mole fraction of a gas is basically the fraction of the gaseous molecules that are present for that particular type of molecule in a mixture. So mathematically speaking, we can express it as this: X1, right, which is a mole fraction of gas 1, is equal to the number of moles of that gas divided by the sum of the moles of all the gases in that mixture, all right? So that's basically the definition of mole fraction. And you should note that because you have moles here and moles here, the mole units will cancel out. So therefore, the mole fraction will have no units, right? So let me put here for emphasis, no units. There are no units associated with the measurement or calculation of mole fraction, all right? Another thing I want to say here is that because the pressure is directly proportional to the volume, if you go to the ideal gas equation, PV or P is equal to nRT over V, right? You should recognize that the pressure is directly proportional to the number of moles if the temperature and the volume are constant, right? So basically, this arrangement here that we have for mole fraction can, or this is not the only way that we can calculate mole fraction. Let me just put it like that. Another way of calculating the mole fraction is what you see right here. The mole fraction is equal to the pressure of gas 1 in a mixture divided by the sum of the pressures of the gases in the mixture, right? So even though this is the actual definition of mole fraction, right? That's the actual definition. We can also calculate the mole fraction based off the pressures of the gases in the mixture, all right? And therefore you can also rearrange this equation to get this here. The pressure of gas 1 is equal to the mole fraction of that gas divided by the total pressure of that gaseous mixture, all right? So that's basically what the mole fraction concept is all about. So based on what we have learned here, on the previous slide, we can do this example. It says the main components of dry air by volume, and it gives you some numbers. Nitrogen is 78.08%, oxygen is 20.95%, argon is 0.93%, and carbon dioxide is 0.04%. So the question is asking, what is the partial pressure of each gas in a sample of dry air at 1.00 atmosphere? So the equation we can use, since we just talked about it, is that the pressure of a particular gas is equal to the mole fraction of that gas times the total pressure of the gaseous mixture. So in this particular case, PT would be the 1.000 atmospheres. The mole fraction would be the percentages here. Even though the question says that the percentages are by volume, volume is also directly proportional to the number of moles, right? So therefore, these percentages can also be mole fraction values as well, right? So therefore, we can start off with nitrogen. The partial pressure of nitrogen is equal to the mole fraction, which is 78.08%, which is 0.7808 times the total pressure, which is 1.000 atmospheres. So this will give you 0.7808 atmospheres. We do the same calculation for oxygen, which is percentage, which is the same thing as 0.2095 times 1.000 atmospheres. So this is going to give you 0.2095 atmospheres. And then in the case of the next gas, which is argon, the partial pressure of argon is equal to 0.93%, which is the same thing as 0.0093 times 1.000 atmospheres. And that would be equal to 0.0093 atmospheres. And then the final gas is carbon dioxide. So the partial pressure of CO2 is equal to 0.04. I'm sorry, divided by 100. So that should be, I'm sorry about that. Let me erase this here. So that should be 0.0004 times 1.00 atmospheres, and that would be equal to 0.0004 atmospheres. And that basically gives you the answers. What I just did are the answers to the question. The question is asking for the partial pressure of each gas in a sample of dry air, given the pressure of the total sample is 1.00 atmospheres, right? One other thing I want to add to this is that when you're doing problems of this type, you can check to make sure that your final answer is valid. In this case here, when you add up all these pressures here, you should get 1.000 atmospheres, right? If you don't get this exact value, you should get a value very close to it, all right? Because sometimes, you know, there are some rounding issues that can take place which could cause the final answer when you add them up to deviate from what it should be, all right? When you add up all the partial pressures, it should be equal to the total pressure, all right? And another thing I want to say here, which I should have mentioned before, is that the sum, let me write this down here, the sum of the mole fractions in a mixture, is equal to 1 always, right? So if you have the mole of, if you can calculate the moles of different substances, you can check to make sure that those moles values are valid by simply adding them up, and it should be equal to 1, all right? Those are just some things you can do to check to make sure that you're on the right track. Okay, are there any questions about this particular example? Any questions? Any questions? Okay, now one of the things that we can use Dalton's law to help us to do is to determine the pressure of a gas that is collected over water. Now, there are some gases that would allow us to do that, right? I can think of oxygen as one example. Other examples would be hydrocarbon gases like methane, ethane, and so on, all right? So you can have an experiment set up where you generate or produce this gas, and then you have a hose leading from that gas, as you can see in this diagram here. We're using oxygen as our example right here. So that gas can be led into this jar here, which is inverted. Now, previously, this jar would be completely filled with water, right? So as the gas is led into that jar, basically because the gas is insoluble in water, it starts collecting above the surface of the water, right? And as you produce more gas, the gas that is produced here, in this case oxygen, will basically exert pressure, which forces down the liquid level in the jar. And ideally, what we try to do in the lab when we're doing this is that we try to basically have the liquid level being forced down until the liquid level inside the jar is equal to the liquid level outside the jar, all right? I'm sorry about that. So the reason why we do that is because we want to make sure that the total pressure inside the jar is equal to the barometric pressure that is exerted on the surface outside the jar, all right? That makes our calculations for the pressure of the gas inside easier to determine, as you're going to see shortly. But before we get to that calculation, here's a question that is being asked here. The question says, what two gases, right, are present above the water level inside the jar? Now we know that one of them is oxygen, right? Oxygen is being generated and led into the jar. So we know that one of the gases here that is collected above the surface of the water inside the jar is oxygen. So my question to you is, what do you think the other gas is? Anybody?
Carbon?
I'm sorry?
Carbon? Maybe?
No.
Okay, I was just guessing.
Well, let's think about it. You have oxygen here, right?
Oh, hydrogen?
I'm sorry?
Hydrogen?
Nope.
No.
Oxygen here, and it's collected over water. So what do you think the other gas here would be? Anybody? I'm actually giving you the hint by saying what I just said. You have oxygen being collected here over water. So what would be the other gas that you'd expect to be present here?
It could only be hydrogen and
Nope.
oxygen, right?
Nope, not hydrogen. Oxygen is one of the gases, but the other gas is, I literally gave you guys a hint. It's collected over water. Come on, guys.
Like evaporated water? Is that what you're
Exactly. Water vapor, right? So the
Yes.
gases that are collected would be water vapor and oxygen. And yes, water vapor and oxygen, H2O in the gaseous state and oxygen, all right? So we call this a wet gas. In other words, it's saturated with water. The oxygen is saturated with water, right? So how do we calculate the pressure of the oxygen that is determined here? Well, based on Dalton's law, let me write this down here. The total pressure of that mixture would be equal to the pressure of the oxygen plus the pressure of the water vapor, all right? Now, how do we determine the total pressure? Well, remember I said that the total pressure here will be equal to the barometric pressure, right? So you can measure the barometric pressure by using a barometer. Remember that instrument we talked about when we just started this chapter? So we can replace PT with P bar, or P bar is equal to PT, right? So therefore, if we have the barometric pressure, and if we know the water vapor pressure, then we can easily calculate the pressure of the oxygen. Now, you might be asking, how do we determine the water vapor pressure, right? Well, there are actually tables that are provided which gives you the vapor pressure of water at different temperatures. And if I'm not mistaken, I think I've posted, let me check. I'm sorry about this. Let me go from here. Okay, screen sharing has stopped. Let me go to Canvas. Let me go to files and let me go to tables. I think I may have posted a table. If not, then I need to provide that to you guys. Let me see. Okay, seems as if I did not. Let me just check another file here. Oh, wait a minute. I saw that already. Fundamental constant. I don't think it's in that. Nope. Okay, yeah. Okay, what I need to do, I'm going to provide that for you later on today. So you can look out for that. But there are tables. Let me go back to the PowerPoint here. Let me go back to this. Let me share my screen. Okay, you can see my screen, right?
Yes.
Okay, so yeah, there are tables. Okay. Oh, you know what? Let me, hold on. Okay. Yeah, there are tables that have been provided, and I'm going to publish it in Canvas so that you'll have it to look at, which gives you the different vapor pressures of water at different temperatures. So as I was saying before, P bar will be equal to P oxygen plus P H2O, all right? So basically, if we have the vapor pressure of water at the particular temperature and the barometric pressure, then we can rearrange it to get this equation right here. So this equation here, P bar minus P H2O is going to be equal to the pressure of the gas, which in this example is oxygen, all right? So that's how we can determine the pressure of a gas in this kind of setup, all right? So the next slide, I believe, is an example of a question which what we just talked about will apply. So the question says, hydrogen produced in the following reaction is collected over water, which has a vapor pressure of 19.8 millimeters mercury at 22 degrees Celsius, when the barometric pressure is 742 torr, and it gives you the balanced equation, fortunately. They could have given you an unbalanced equation, or they could have given you the description of the equation, and you'd have to figure out the equation. But in this case, they were kind enough to provide the balanced equation. So the question is asking, what volume of the wet gas will be collected in the reaction of 1.50 grams aluminum with excess HCl, all right? Okay, so there's no space provided here. So what that means is go to my writing board here. And I think you may not be able to see it. So that means that I need to go back here and share that screen. Okay, I take it you can see my screen, right?
Yes.
Okay, so the question gives you, okay, let's see what the question gives you. The question says, what volume of wet gas will be collected in the reaction of 1.50 grams aluminum with excess HCl? Okay, so the first thing I would do is try to find the vapor pressure, or I should say the pressure of the hydrogen. And based on what we just discussed, the pressure of the hydrogen would be equal to the barometric pressure minus the pressure of the vapor pressure of water. So the barometric pressure is given as 742 torr minus the vapor pressure of water, which is 19.8 millimeters mercury, which is the same thing as torr. All right. So when I did that calculation, let me do it now actually. 742 minus 19.8, according to my calculations, this works out to be equal to 722 torr. All right. So that's the pressure of the hydrogen in that gaseous mixture. All right. Now the question gives you, let me see here, 1.50 grams of aluminum. Okay, so basically you're given 1.50 grams of aluminum and you're asked to determine the liters of H2 in the mixture. So we start off with the 1.50 grams of aluminum, and we're going to multiply by, we're going to convert it to moles. So 1 mole of aluminum will go up top, and down here would be the molar mass of aluminum. So I need to go to my, well, if I remember correctly, and I don't have my periodic table here with me, so let me go to the periodic table in Canvas, which I think I've already downloaded, or maybe not. Let me see. No. Okay. So, let me download it. Make life easier. Oh, here it is. All right. And so for aluminum, the molar mass is 26.98. So I'm going to put 26.98 grams of aluminum. And then I'm going to look at the mole ratio between the aluminum and the hydrogen. And based on the given equation, it's 3 moles of hydrogen for every 2 moles of aluminum. All right. So I'm going to do this calculation. 1.5 divided by 26.98 equal times 3 divided by 2. So according to my calculation, this works out to be equal to 0.0834. 834 moles of hydrogen, right? And then based on the ideal gas equation, we can determine, let me see here. We can determine the volume of the gas, V is equal to nRT over P, by plugging in the number of moles, which we calculated here, which is 0.0834 moles, times R, which is 0.0821 liters atmospheres, over mole Kelvin, times the temperature. What's the temperature? According to the question, the temperature is 22 degrees Celsius. So that's 295 Kelvin, 295 Kelvin, all multiplied by the pressure. And that would be the pressure of the hydrogen that we calculated here, all right? Which is 722 torr, but we have to convert that to atmospheres. 1 atmosphere over 760 torr, all right? So the mole units will cancel out here and here, the Kelvin will cancel out here and here, the torrs will cancel out here and here, atmospheres will cancel out. So we're left with the answer in liters. So let me do the calculation. 0.0834 times 0.0821 times 295 divided by 722, which itself is divided by 760. So according to my calculations, rounded off to 3 sig figs, the answer here would be equal to 2.15, and the units would be liters. And that's how that example would be done, all right? Any questions about this? Any questions? Any questions? Okay, so let me go back to the PowerPoint. Okay, so come on. All right, so what time is it, by the way? I'm losing track of time. Oh, 10:17. All right, we have enough time to cover some other things. All right, so let's talk about in more detail the kinetic molecular theory, right? We were introduced to it earlier in this chapter, but we're going to look at some quantitative aspects of this theory. So what you see here on the screen is basically all the principal assumptions of the kinetic molecular theory. First one says that a gas is made up of molecules that are in constant random straight line motion. So these gas particles, molecules, whatever, they're always moving, they're high energy. Their movement is basically mostly translation. And in fact, the only way that they deflect from that translation motion is if they bump into each other or if they bump into the walls of the container, right? The second assumption of this theory is that the molecules of a gas are on average far apart from each other. So therefore, if you have a sample of gas that is in a vessel, then what you're looking at is mostly empty space because the mean distance between the gas particles are relatively far from each other. The third one is very important, and I think I alluded to it earlier in this class. There are no intermolecular forces that exist between the particles except when they collide with each other, right? So basically what this is saying is that the gas particles are acting independently of each other. And that was what I made reference to when I was talking about Dalton's law, right? Even if you have a mixture of two or more gases, the different particles are so energetic that they do not have any influence on each other, all right? And then the fourth assumption is that individual particles may gain or lose energy as a result of collisions. However, the total energy of that gaseous collection of particles remains constant. And if I remember correctly, there's a term in physics that is used to describe these collisions. We say that these collisions are elastic, all right? So what this means basically is that if you have the particles moving around and they bump into each other, there will be 100% direct conversion of energy from one particle to the next. There will be no net loss of energy. And therefore, as a result, when you look at the total collection of particles in a gas sample, the total energy remains constant. And of course, that is true if the pressure is constant, the volume, temperature, all those factors are constant, all right? So those are the principal assumptions of the kinetic molecular theory. Now, based on those assumptions, and I won't go into the math of this, I remember doing this when I was a student, and that's because I minored in physics. In physics, we had to learn how to do this. You can actually derive an equation which looks like this, right? And this equation basically shows you the relationship between the pressure exerted by a gas particle and some other terms. And this equation is directly derived from the assumptions of the kinetic molecular theory, right? So just to highlight what these different terms represent, P represents, of course, the pressure. V here represents the volume. This uppercase N here represents the number of molecules. This N here represents the mass of each molecule. And this term here is called the average of the squares of the speeds of the molecules. So what that means, let me just write something up here. This means the mean square average of the speeds of the molecules. All right. So the way this is calculated is as follows. This is equal to the square of the velocity of gas molecule 1, plus the square of the velocity of molecule 2, molecule 3 squared velocity, and so on to the nth molecule. All divided by the number of molecules, right? So that's what this represents, right? And that's what is here in this equation, all right? So, as I said before, this equation can be derived directly from the kinetic molecular theory. And there's some interesting relationships between the different terms, which actually is confirmed by different gas laws that we looked at earlier. For example, you'll notice here that there's an inverse relationship between the pressure and the volume. If everything else is constant, then the pressure of the gas, based on this equation, is inversely proportional to the volume. So that is basically confirmed by Boyle's law. That's basically what Boyle's law says. The pressure of a gas is inversely proportional to the volume. Another relationship that is shown here is that the pressure of a gas is directly proportional to the number of molecules of the gas. And that is what Avogadro's law was saying, all right, that we talked about earlier. And then we have this relationship between the pressure of a gas and the mass of the molecule, right? And basically what this suggests is that the heavier the molecule, the greater the pressure exerted by the gas, all right? Which makes sense. You'd expect that the heavier molecule, everything else being the same, would hit the walls of the container harder, and therefore that would result or manifest in an increase in pressure of the gas that is exerted against the walls of the container. And then of course, the root mean squared speed term here, basically what this is saying is that the pressure of a gas is directly proportional to the root mean squared, the square of the root mean squared speed, all right? Well, actually the root mean squared speed. So basically what this is suggesting is that the faster on average a molecules, the greater would be the pressure exerted by the gas. Again, that makes sense based on the kinetic molecular theory. Basically, the faster the gas molecules move, the harder and the more frequent it would hit the walls of the container, exerting greater pressure as a result, all right? So that's basically what this equation is telling us. Now, let me just say that you don't need to know this equation. In fact, I don't even anticipate you using this equation here, but I thought it was important for me to show you this so that you understand that this equation, firstly, is derivable from the kinetic molecular theory, and this equation also establishes the different types of relationships between the variables that I just discussed, all right? Now, the next slide shows you another equation, which is derived from this equation, right? So basically, this equation shows you the relationship between the average kinetic energy of a gas to different terms. R, which is the molar gas constant, Na is Avogadro's number, and T here is the temperature. Now, of all the terms on this side, T is the only variable. So therefore, what this is suggesting is that there's a linear relationship between the kinetic energy and the temperature of the gas. So we can simplify this equation to kinetic energy is equal to a constant, which is basically this collection of constants here, multiplied by the temperature, all right? So again, this is confirmed by what we know how gases behave. As you increase the temperature of a gas, the kinetic energy of the particles increases, right? So that's basically what is stated here. Of course, the temperature here must be expressed in Kelvin. So that's why they stress here that the temperature is expressed in Kelvin, all right? So this is another equation, which again, you don't need to know or memorize, but it shows you, again, the relationship, in this case, between the temperature and the kinetic energy. Okay, any questions so far about the kinetic molecular theory? Okay, so let's talk about molecular speeds. I think this would be the very last thing we're going to discuss for today, all right? So, as you can imagine, right, you can, of course, use your imagination. You will immediately recognize that when you have a collection of gas molecules in a container, at any instant, they won't be traveling at the same speed, right? You have some gas molecules which are slower in terms of the speed. There are other gas molecules which are much faster. And then you have basically the bulk of the gas particles which will be traveling at about the average speed, right? So as stated here, there'll be a wide distribution of speeds for any sample of gas molecules, right? So the average that we use to represent the speeds of the gas molecules is what I mentioned before, the root mean squared speed, right? And in fact, the root mean squared speed is basically the square root of the sum of the squares of the speeds of all the gas particles divided by the number of gas molecules, right? So if you remember the equation, let me rewrite it here again so that you can have it to look at on this page. The average squares of the speeds of the molecule will be equal to the square of gas molecule 1 plus the square of gas molecule 2 plus the square of gas molecule 3 and so on. Oops, I'm sorry. Let me erase this here. And let me go back to my pen function. Plus dot, 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 square of the speed of gas molecule n, right? And then we divide all of that by n, all right? So that's what this is, which is what this is, right? So to get the root mean squared speed, you'd have to put all of this here where this is, all right? And it turns out that this root mean squared speed is equal to square root of 3RT divided by m, right? Now, the different terms in this equation, you know some of them already. R is a molar gas constant. Let me circle it here. R is the molar gas constant. T is the temperature in Kelvin. And M is the molar mass, right? Now, let me just say something about the R in this case and the M in this case. If you remember, we said that R is equal to 0.0821 liters atmospheres over mole Kelvin, right? And you should recall that there are other ways of expressing R's depending on the units that you're using here. So in the case of this value here, the units of R would be liters atmospheres over mole Kelvin. However, there's another value of R, which is 8.31, and the units for that would be joules per mole Kelvin. And that's a value of R that you're going to use here, all right? And there's a reason for that, which I'm going to explain shortly, all right? But please note that the value for R that you're going to use in this equation here is 8.31 joules per mole Kelvin, all right? Now, another thing I want to mention is that in the case of molar mass, we're all familiar with the units of molar mass being moles, grams per mole, all right? So that would be the units of molar mass that you'd use in most cases. However, in this case, we would have to convert grams per mole to kilograms per mole. And that would be the value expressed in kilograms per mole that you're going to use here, all right? So please note the R value must be 8.31 joules per mole Kelvin, and the value for the molar mass must be expressed in kilograms per mole. So if you take care in making sure that those are the units that you're going to use in this equation, then what you're going to see is that the units for the root mean squared speed is going to be meters per second, all right? Now, let me explain why that is by my writing tablet here. Up. And I guess I have to share. Okay, where is that? Oh, right here. Okay. All right. So remember the equation I gave you was the root mean squared speed, RMS, is equal to the square root of 3RT over the molar mass. All right. Okay. Now, let me explain why I mentioned the different unit changes that you need to make in order to use this equation. So what I'm going to do is basically carry out the same algebraic arrangement here, but I'm just going to use the units, right? So in the case of R, well, the 3 here has no units, so there'll be no units for that. But in the case of R, remember I said that the units here must be joules per mole Kelvin, right? The units of temperature would be Kelvin, and the unit of molar mass must be kilograms per mole, all right? Now, one thing I need to mention here, and you're gonna see this, unfortunately you won't see this until the next chapter, chapter 6. The joule unit is the same thing as kilograms meter squared over second squared, right? So if you plug this collection of units where the joule is here, you're going to end up with square root of kilograms meter squared over second squared times Kelvin divided by kilograms. I'm sorry, I forgot to include mole Kelvin here, mole Kelvin, right? Times Kelvin divided by kilograms per mole, all right? So all of this will be under the square root sign, and then you're going to see some units canceling out. You're going to see, for example, that the kilograms will cancel out here and here, the mole will cancel out here and here, the Kelvin will cancel out here and here. So what you'll be left with is the square root of meter squared over second squared, which is the same thing as meters per second, all right? So that's the reason why we have to make sure that the units of R is joules per mole Kelvin, and the actual value here would be, as I said before, 8.31, and the unit of molar mass here must be kilograms per mole. Once those units are in place, then the resulting units of the root mean squared speed of the molecules of the gas will be meters per second. All right, I hope that is clear enough for you. Any questions about this? Any questions about what I just discussed? Okay, so, so let me go back to the PowerPoint and let me start sharing that. Okay, so one last thing I want to say before I move from the screen. Based on this equation here, you can see that there's some relationship between the root mean squared speed and the temperature and the molar mass. Remember, R is a constant, right? And the 3 here is also a constant. So basically what this equation is suggesting is that the greater the temperature, the increase in temperature here, as you increase the temperature, the average speeds of the molecules would increase. Of course, that makes sense in light of the kinetic molecular theory, right? Also, down here, as the molar mass increases, then the root mean squared speed decreases, right? Which again makes sense if you think about it, because what the molar mass basically represents is how heavy the molecules are, right? Remember, the molar mass is the same thing numerically as the atomic mass or the molecular mass, right? So therefore, what this suggests is that the heavier the molecules, the slower will be the speed of the gas particles if the temperature is the same, all right? Okay, so that's as far as some introduction into the whole concept of molecular speeds. Now, I want to show you this graph here, or these 2 graphs, which gives a pictorial representation of some of the things that we talked about. So let me rewrite this equation up here. Root mean squared speed is equal to the square root of 3RT over M, all right? Okay, so keep this equation in mind as we're discussing these graphs. So let me explain what these graphs are all about. This graph here is a plot of the relative number of molecules on the y-axis versus the molecular speeds on the x-axis, all right? And this is for 3 different gases. I don't know if you can see the colors, but this pink line here, this pink curve here, is the distribution curve for oxygen. This, I think it's blue line, is the distribution curve for methane. And this purple line here is the distribution curve for hydrogen, all right? Now, as far as the root mean squared speed is concerned, the way you can determine that from the graphs for each gas molecule or each gas is that you drop a horizontal line from the peak of the curve to where the x-axis is. So I don't have a ruler to do this, so let me just do this freehand. Oops, So in the case of oxygen, you drop a vertical line, and as you can see, I'm doing a horrible job already, so please forgive me. You drop a horizontal line from the peak of the curve to where it cuts the x-axis. So by my estimation, and I'm just guessing here, or guesstimation, whatever, this is 1,000, so this must be 500. So I'm estimating that the root mean squared speed for the oxygen molecule is 400 meters per second, based on what I just did, dropping the vertical from the maximum point here to the x-axis. And then in the case of methane, I'm doing the same thing, dropping a vertical here. I think I'm doing a better job on this one. So this looks like, I would say this is about 800, whoops. 800 meters per second. And then in the case of hydrogen, well, hydrogen is easier to determine because if this is 1,000, that means this is 1,500. So in the case of hydrogen, that would be about 1,500 meters per second, all right? So how does this help us in terms of understanding this equation? Remember, this equation gives you an inverse square root relationship between the molar mass and the root mean squared speed. Now, the molar mass of oxygen is about 32. The molar mass of methane is about 16. And the molar mass of hydrogen is about 2, right? So you can see that as you go from 32 for oxygen to 2 for hydrogen, there's a decrease in the molar mass, right, which is this here. And there's a corresponding increase in the root mean squared speed from 400 in the case of oxygen to 1,500 in the case of hydrogen. So that this plot here is actually verifying that the heavier the molecule, the greater would be the root mean squared speed, as long as the temperature is constant, which it is. The temperature is constant at 273 for each of these gases, all right? So that's how this graph explains, or well, not explains, but basically shows the relationship between the root mean squared speed and the molar mass of the gas. Now, let's look at the graph on the right. The graph on the right is showing you, it's the same plot, number of molecules versus the speeds, but the only difference is it's one gas, not different gases, one gas, and that gas is oxygen at different temperatures, all right? So this is at 273, and then when you raise the temperature to 1,000, the curve becomes this, and when you raise it to 2,000, the curve becomes this, right? So at 273, as we said before, the root mean squared speed is 400, right? In the case of 1,000, if you drop a vertical down here, let's see what that gives us. That looks like about, I would say 700. I could be wrong, but I'm going to go with that, right? And then now in the case of at 2,000, this is the peak right here. So if I drop a vertical down here, okay, this is 1,500. So this is just shy of, I would say this is 1,400, all right? Okay, so as we can see here, as you go from 273 to 1,000 to 2,000 Kelvin, the temperature, or I should say the speeds, the root mean squared speed increases from 400 to 700 to 1,400 respectively. So as the temperature increases for the gas, the speed increases. And again, this falls in line with what the kinetic molecular theory is saying. Gases are moving at the gas particles are moving at high energy, high speeds. So if you impart more energy to the particles will move at higher speeds, all right? And therefore will increase the pressure of the gas, all right? So that's basically for all that we have to say, unless you have any questions, but basically this explains, or I should say show graphically, the relationship between the root mean squared speeds and the molar mass. That's for the plot on the left, and the relationship between the root mean squared speed and the temperature, which is what the plot on the right is showing, all right? Okay, any questions about what I just discussed with respect to the graphical plots of molecular speeds? Any questions about this? Any questions? Okay, so let me see what time it is. You know what? I'm going to stop here because this next topic and the other topics will take a bit of discussion. So we're going to stop here for today. So are there any questions otherwise that you guys have before we leave? Any questions in the next 4 minutes? Any questions?
No questions for me.
Okay. All right. Well,
Okay.
that's it for today. I'm sorry? Did somebody say something? I thought I heard somebody saying something.
No questions for me either.
Okay, all right. So that's it for today. I'll be available for office hours today from 1 to 4. If you have any questions, any individual questions that you don't want to ask here, you can contact me on Skype concerning that. All right. So until next time, enjoy your day, the rest of your day, and I'll see you guys on Thursday. All right. So take care.